Good morning, good afternoon. It's Matteo Centia here, and welcome to the Computational Mechanics course. Today's lecture number 4 in the module, will deal with the constant strain triangle finite element. In particular, today we will learn why. You see this finite element model behind me? You can see that each triangle is colored with the same color, so there is no gradient of color within each triangle. This means that the stress inside this triangle is constant. So how can the stress be constant inside this element? Well, it's because the strain is constant, and that's why the name to this type of finite element, the constant strain triangle. So we've seen last week the general framework of the finite element method, and we saw the importance of the discretization approach, and in particular on the model for the displacement, which was strongly dependent on the nodal displacement vector of our finite element, and in particular on these shape functions that rule in the end how the displacement inside each element evolves, and therefore, given the displacement, the strain. So today we will introduce the constant strain triangle CST finite element. We will determine the shape functions of this particular finite element, look at the graphical representation of CST shape functions, how we get the strains, the stiffness matrix, and the equivalent nodal load vector for body forces or surface pressures, and look at an example of this latter approach. Okay, so let's consider this finite element in its local coordinates xy with nodal coordinates of node 1, 2, and 3, x1, y1 for node 1, x2, y2 for node 2, and x3, y3 for node 3 of area A. We are working in 2D, so it's a 2D problem, so the dimension is equal to 2, and therefore our displacements will be a 2 by 1 vector, ux and uy. The deformations will be a 3 by 1 vector. We will have epsilon x, epsilon y, and gamma xy, hence stresses 3 by 1, sigma x, sigma y, and tau xy, and the stiffness matrix for 2D problems we've seen plane stress and plane strain is a 3 by 3 matrix. Last week we've seen the displacement model for finite element formulation, and we've seen that the displacement of any point inside our finite element can be written as a function of the nodal displacement vector. So any point in FE can be described by means of this matrix, interpolation matrix, that is the shape function matrix. So given the nodal displacement vector, represented here by these black arrows, so ux in node 1 and uy in node 1, etc., we can then obtain ux and uy for any point in here. To do that, we need the shape function matrix. And what is this equal to? Well, the content of this lecture is the determination of this, from which then we can calculate the strains, the stiffness matrix of the element, and the nodal displacement vectors. Equivalent nodal load vectors. Okay? So the general way to determine the shape function matrix was to introduce some parameters and write our displacement as a function of some constants, which at the moment we don't know. And in this case, we will use 6 parameters and have a linear function of, so describe the displacement in x, for example, as a linear function of the position x and y. The same for the displacement in y will be a linear function of x and y through these 6 parameters. So we can basically write that ux is a matrix n star times this vector of alpha parameters. Now, imposing consistency at the nodes, meaning let's write ux at position x1 and y1, that is the coordinate of node 1. Well, it will be alpha 1 plus alpha 2 x1 plus alpha 3 y1. This is what? Well, it should be equal to ux of node 1, and so on. What does this mean? This is the nodal displacement vector. So this is equivalent to write psi times alpha is equal to the nodal displacement vector ue. Okay? By inverting this matrix here, so I multiply left and right hand side by psi to the minus 1, this cancels out, so I'm left with alpha is equal to psi to the minus 1 ue. Substituting this up here, we can again obtain that the shape function nx, so n is a function of the position, is equal to n star times c to the minus 1. Okay, so this is we've seen this last week in general terms. This time we have a linear relationship of in terms of x and y. Okay, so in the constant strain triangle, we can also obtain the shape function by just observing how this displacement model looks, and considering that the displacements are linear function of x and y. Okay, so u inside the element at any position is n times ue. So n will necessarily have to look like something like this, where we have n1 0, n2 0, and 3 0, meaning that ux is equal to n1 times ux in node 1 plus 0, because it will not depend on uy, it just depends on the x displacement, n2 times ux2, and n3 ux3. Oh, sorry, here there's a typo, it should be a 3. I'll correct that later. But this means that ui, on the other hand, is n1 times ui1 plus ui2 times n2 plus ui3 times n3. We can write this in, let's say, condensed form, where we write that ux in any position in the element is the sum between of j going from 1 to 3 of nj, so n1, n2, and n3, xy of uxj. Okay, the same for ui. So for each shape function, we can enforce consistency conditions. What does this mean? Again, if we write ux in x1 and y1, we have n1 in x1, y1 times ux1 plus n2 in that position, ux2 plus n3 is equal times ux3 is equal to ux1. So we can immediately see that the only way this would work, if looking at the first line only, is if n1 in this position is 1. In fact, n1 in the position of node 1, so x1, y1, is equal to 1 and must be equal to 0. N1 should be 0 in the other, in x2 and x3, whereas n2 is equal to 1 when we're looking at node 2, whereas should be 0 in the other nodes. And finally, n3 should be equal to 1 when we look just at node 3, but 0 in the other nodes. Okay, so moving on to determination of this, the rest of also these parameters alpha, beta, and gamma. We can find the coefficients for the three shape functions using this approach. Okay, so let's do it for j equal to 1. So let's calculate n1. Okay, and well, k will be 1, 2, 3, because we will look at alpha, beta, and gamma. Okay, so n1 in x1, y1, we said is equal to alpha 1 plus beta 1 x1 plus gamma 1 y1 is equal to 1. n1 in node 2 was equal to 0, and n1 in node 3 is equal to 0. So this means that we can write this in matrix form by grouping alpha 1, beta 1, and gamma 1. So this means that alpha 1 plus x1 beta 1 plus y1 gamma 1 is equal to 1. Then we have alpha 1 plus x2 times beta 1 plus y2 times gamma 1 is equal to 0, and so on. So how do we determine alpha, beta, and gamma 1? Well, we have to invert this matrix and so multiply by the inverse on both sides. What does this mean? So if this is this vector, and let's color this as this matrix here. If we multiply left and right by the inverse, which I color in the dark blue, then this will cancel out with that, and we're left with the inverse of that. Now, this is a matrix that we can calculate. You can use online mathematical software and you can invert this matrix. You'll see it's a very complex matrix. But anyways, alpha 1 is what? Well, alpha 1 will actually be this little term here, because this times that, all these other terms are 0, so you're left only with this term. So alpha 1 is the term you have in the top left corner of the inverse of this matrix here. In the same way, beta 1 will be this term, and gamma 1 this other one. Okay? So by doing that, by calculating the inverse of this matrix, we obtain that alpha 1 is equal to a1 over 2a, beta 1 is equal to b1 over 2a, gamma 1 is equal to c1 over 2a, where a is the area of the triangle, and this is because the determinant of this matrix over here is actually equal to 2 times the area of the triangle. So this a1, b1, and c1 terms, okay, if we repeat for j2 and 3, we obtain all of them, and we can then therefore calculate the shape functions in their final format. They look like 1 over 2a times aj plus bjx plus cjy, where a, b, and c are represented here. Okay, so this is the shape function for the constant straight triangle. And if we move on to the next slide, we can see that the graphical representation is pretty simple. So n1 will look like, is actually the description of this plane, okay, where according to the position xy inside the element, n1 will assume the value of this projection. Okay, so when x, y are in this point, n1 is 1. When x, y were in this point is 0. Along all this line will be 0 until there. And the same for n2. So n2 will be equal to 1 when the coordinates are on node 2, whereas it will be 0 when we're there. And finally the same for n3. So given this graphical representation, in fact, the shape functions can be easily calculated for our hand calculations, considering this statement that, and you can read later on when you pause the video, but looking at this diagram. For example, let's do a little example by hand. Okay, let's imagine we have a constant strain triangle that looks like this, of length L. These are nodes 1, 2, and 3, and L in the y direction. I want to calculate n1. So n1 is equal to 1 when I'm here, but is equal to 0 on this line. So what I do, I write the equation of this line here. Y is equal to minus x plus L. Then I take the y on the other side, and I write that L minus x minus y is equal to 0. So I'm always equal to 0 here. And I multiply this equation by a constant. And then I say my n1 is this, c, which is the constant I have to find, l minus x minus y, which is this equation. And then I pose the consistency at node 1. So n1 in position 0, 0, I substitute 0, 0 here, and I get that it's equal to c1 times l. Should be equal to 1, because n1 in this point is 1. Then what happens is that I can calculate the displacement. I calculate c1 as 1 over L, and if I substitute this to the generic equation up here, I get that the shape function n1 will look like this, L minus x minus y over L. Let's try. When x is 0 and y is 0, L over L is 1. When x is equal to L, y is equal to 0. So L 0, L minus L 0, 0, yes, it's correct, it's 0. And this was for n1. What about n2? Again, n2 is this node here, is equal to 1 when I'm on this node. So I look at the opposite and I write the equation of this line, because this should be always 0 for n2. And this equation is x is equal to 0. So c2x will be my generic n2 shape function, and I impose consistency. So when I'm in this point here, L is equal to 2, sorry, x is equal to L in this point, and y is equal to 0. I substitute the value and I obtain C2L is equal to 1. In this way I can calculate the constant C2 as 1 over L. I substitute and I get that N2 is x over L. Finally, I can do this for the third shape function, N3. I write the equation of this line here, and as I did for these two, I can obtain the constant and the shape function N3, y over L. Okay? So this is the way we can obtain shape functions for simple geometries, like in the end of the day our hand calculation problems that we will see next week. Okay? So having obtained the three shape functions, we can then obtain model for strains. In fact, we know that the strain is equal to this differential operator times the displacement. But this displacement inside the finite element is NUE. So we can then obtain our B matrix, that was basically the differential operator times our shape function. And this in generic terms, but now we have actually calculated our shape function for the CST. So let's calculate what this operation looks like. Well, this means this is a 3 by 2 multiplying a 2 by 6, so we'll get a 3 by 6 matrix, and this times that gives us n1 derivative in x, and then this times that gives a 0, and then this times that is n2 derived by x, and this times that is a 0, and this times that is n3 derived by x, and this times that is a 0. Then the second line will be this times this is a 0. This times that is n1 derived by y, etc. So we have to differentiate n1 and n2 by x and y and fill this matrix. So given our generic shape function nj that looks like that, nj derivative in x is basically 1 over 2a, and I differentiate this by x, I'm left only with bj. Whereas nj derivative y is I differentiate this respect to y, and I remain with 1 over 2a cj for j 1, 2, 3, where a, b, c 1, 2, and 3 look like that. Okay? And the area of the triangle is there. So if I substitute then these terms in here, I can obtain that the strain is equal to BUE is equal to 1 over 2a, which basically it's over here. 1 over 2a stays out of this matrix. This is the B matrix, and then I have B1, B2, B3, according to the value of J I have, times the nodal displacement vector. So we have the strains inside our element, and what's the stiffness matrix of our element? Well, we have the displacements are n times nodal displacement vector. The strains are B times UE. And then if you look at the definition of the stiffness matrix, this should be, look at the previous lecture on the finite element method. We know that the stiffness matrix of the element KL is the thickness times BdB, okay? And so we can then calculate its dimensions. Since B is a 6 by 3, D is a 3 by 3, and B transpose is a 3 by 6, then K will be a 6 by 6. Now, we don't need to always calculate all the terms, and you will see later on when next week we do a problem. So sometimes it's not necessary to calculate 6 by 6 terms, but just calculate the ones we need. So how do we calculate only the terms of the stiffness matrix that we need? Well, we calculate them like this. So each coefficient Kij of the element can be computed directly. So this is KLij is the thickness T integral over the area of the sum from 1 to 3 of Rs Bri dRs Bsj in the A. Let's do an example to understand what this means. So let's calculate Ky1. So this term here. So I is equal to 1, j is equal to 1 to have Ky1, 1. This means that we have to do the integral, well, thickness T times the integral over the area of the sum of Rs that go from 1 to 3. So we have Br1 dRs Bs1 in the A. This means the sum of, well, Rs is equal to 1. We would have B11 squared D11 for Rs, and this is the B squared, because if you substitute R is equal to 1, S is equal to 1, we get B11, and that's the square here, and D11. This is Rs is equal to 2, so D22, and then we have B21 and B21 squared, and then B31 squared, D33. Then KL61, so this term here, well, I is equal to 6, j is equal to 1, is the integral over the area of the sum of this multiplication for Rs that goes from 1 to 3. So what does this mean? Well, again, for Rs is equal to 1, this is what you get. Rs is equal to 2, this is what you get. Rs is equal to 3, and then you have to sum them. So look at this with patience, pausing the video, and try to get and do it yourself. So we can calculate each component individually, okay? And this is important, and we'll see for our hand calculations, we don't want to do all of them. We want to know which one and how to calculate each of them. So the stiffness matrix then of in plane strain and plane stress, we remember that the D matrix could be expressed, and look at the plane lecture problem, as a unique, so where D11, D12, D12 because it's symmetric, and D22 is equal to D11, and D33 here, where we have E bar and nu bar, depending on if we were a plane stress or plane strain problem, okay? So these are the terms D that you need to use when you do DRS. For example, D11, you get this value here, which is E over 1 minus nu squared times 1, where E and nu are one of these two, depending on which type of problem we're solving. So moving towards the end, how do we calculate the equivalent nodal load vector for the constant strain triangle formulation? Well, PL, if you look at the previous theoretical lecture, is defined as represented here. So we have the shape function multiplying the body forces and the integral over the area of the element, whereas the pressure loads on the surface is the shape function transposed times the distributed load on the surface, gamma. So this, if we have f that is in 2D fx and fy, we substitute the n function as transposed as defined in the previous slides. And if you do this multiplication, you obtain that the equivalent nodal load vector looks like this for volume forces and for surface loads. Okay, so basically the shape function can be considered as a sort of weight for the computation of nodal load vectors. Okay, remembering that nj is equal to 1 on node j and 0 when you're not on node j. Okay, so let's see an example to calculate this nodal displacement equivalent nodal load vectors. For example, let's consider this problem here. We have a constant strain triangle finite element of node 1, 2, and 3, and a pressure load on this surface, on this line, from node 2 to 3. So the equivalent nodal load vector, P, is equal to the integral, the thickness T of the element, and the integral of the surface of n1 fx, n1 fy, n2 fx, n2 fy, etc. Now, which of these are going to be 0? Well, this is the node 1, 2, 3. So node 1, fx is 0 and fy is 0. Node 2, fx is 0, fy is not going to be 0, so this goes away. And then and node 3, the x, there's no pressure in the x direction, so this is going to be 0. So we just want to calculate n2 and n3 given the generic shape function equation. So n2 is 1 over 2a, and the area of this triangle is what? L times L divided by 2. And then we have these coefficients, a2, b2, and c2. What do they equal to? Well, we need the coordinates of the nodes. So for example, a2 is x3, y1 minus x1, y3. So we can calculate that for our problem. And n3 again is represented here, and we need a3 and b3. a3 and b3, we can calculate that knowing the coordinates of these points. And this is what is the result. So then if we substitute this in here, we have the integral over the length L of pt over L squared, because f is a p, and this results, the result of this is here, so plt over 2, 0 minus plt over 2, okay? So if you look at it, it resembles something. Yes, it's perhaps what you're thinking. Basically, in general, the nodal load components of distributed loads, when we use constant strain triangle, can be calculated as the reactions of a simply supported beam. So when you have a beam under a distributed load P of length L, we know that the reactions are PL over 2 on both sides, okay? What if we had a triangular load? This would be PL over 6 on one side and PL over 3 on the other, okay? So you can use this directly without going through all this, let's say, general framework definition, and use this directly to calculate the nodal load vector for the distributed surface loads. What about body forces? Again, consider body force F. So PF is the integral over the volume of n transpose dv times fx and fy vector. So it is possible to demonstrate that if you put the origin of our local reference axis in the center of gravity of the element, there is this property here. So the integral over the area of mj dx dy is actually equal to the area of the triangle divided by 3 for all the three shape functions. So using this property, then the nodal load vector for body forces, okay, so forces over volume, is basically evenly distributed on each node. What does this mean? Well, Fy at over 3 on node 3, Fx at over 3 in node 3. So basically F times the area and thickness, this gives the total force because this is F over a volume. So the volume is the area times the thickness. We divide by 3 and we distribute in X and Y 1/3 on each node. So with this, I conclude the constant strain triangle theoretical lecture. We've seen how we determine the shape function for CST. We've seen the graphical representation of shape functions, which is quite handy when we want to calculate shape functions for simple problems as the one we've seen. Strains within the finite element, we calculated the B matrix for the CST, the stiffness matrix for the CST, all 6 terms, or we even saw how to calculate each local each term individually, and it will be handy. We'll see next week why. Finally, to calculate the equivalent nodal load vector when we use the CST, we've seen, let's say, the generic theoretical description, but also this way to consider an equivalent simply supported beam to calculate for the pressure loads, or distributing the body forces evenly to the each of the 3 nodes. With this, I conclude this 4th lecture of the module. I hope you enjoyed. See you next week, and have a good day.